All right, this is the second lesson of Unit 8. Today we're going to be taking our trigonometry and extending it into general angles, not just angles in a triangle. So if we look at a triangle like this and we want to know the tangent of alpha, that symbol is the Greek letter alpha. So if we look at this triangle and we want to know the tangent of alpha, you hopefully remember and know that the tangent is always the ratio of the opposite side over the adjacent side. So for this triangle, if we're looking at the opposite over the adjacent for the tangent, the side opposite alpha is 4, length 4, and this side here is the adjacent side. So the tangent of alpha would be 4 over 3, 4/3. All right, so a little review from last time. But what if we didn't want to know the tangent of alpha? What if we wanted to know the tangent of theta, where theta is this angle shown in red? Well, we've always talked about tangent as being the opposite over the adjacent, but this angle theta isn't inside of a triangle. Uh, there's no opposite side of the triangle. There isn't a triangle that includes angle theta. And that's what we're going to be doing today, is finding a way to define the tangent of this angle theta, or any angle that is not included in the right triangle. And just to whet your appetite, it's going to involve putting our angle on a coordinate system and allowing lengths to be negative, at least in that the negative is telling us a direction. Okay, so, and actually I'll just tell you here that the tangent of theta is going to be negative 4/3. Okay, so we're going to learn, and don't worry about where I got that from. That's what you're going to be learning today, is how to figure out that the tangent of theta is 4/3. Before we can get too much into these angles and triangles, though, we need to talk about uh, angles in standard position. We're not going to be arbitrarily drawing our angles anywhere on our paper anymore. We're going to draw them on a coordinate plane. So here's a little coordinate plane. You've got the x and y axis marked. We're going to call standard position of an angle the position where the vertex of the angle is at the origin, and it has this side here that is on the positive x-axis. That's going to be called the initial side. Initial is like the beginning. And we're going to rotate that angle, because an angle is a rotation. We'll rotate it to here, and the side where that rotation stops is going to be called the terminal side. And so all angles are going to be starting, all of our angles in standard position are going to be starting on this initial side on the positive x-axis. Now, the good thing about defining the standard position for angle is that we can now define negative angle. If an angle is negative, what we will define that as is just rotating the other direction. So a negative angle is going to rotate down instead of up as it rotates. So I just wanted to look at a couple of examples of this. So standard position, again, means the initial side is here. So this one is showing you the angle 135 degrees. So if we rotate 135 degrees, it will take us to that terminal side that's shown in red. And over here we have an example of some negative rotation. So here's our initial side here. If we rotate negative 45 degrees, it takes us to this terminal side here. So I want to sketch a couple more for you. Whoops. So if I wanted to sketch the angle 320 degrees, my initial side would be here, and I would rotate that angle up. This would take me to 90 degrees, keep going to 180 degrees, keep going to 270 degrees, and let's see, I've gone 270. I need to go a little bit more to get to 320, and that little bit more I need to go is 50 degrees more. So this would be my terminal side, and my angle is 320 degrees. So it ends up in the fourth quadrant. If I wanted to sketch the angle negative 225, again, it would start on this positive x-axis right here, and we would rotate in sort of this downward direction. So we rotate down, this would be rotating negative 90. If we keep going, it'll be a negative 180, and we need to go a little bit more to get to 225. So that's our terminal side. Here's our angle, negative 225 degrees. Last one I wanted to show you is if we start here on our positive x-axis and we want to rotate negative 60 degrees, the negative tells me to rotate in that clockwise direction. Negative 60 would be something like this. I'm not going to be super judgy about exactly where your angle ended. Try to get it in the right neighborhood. Okay, so when we have these angles in standard position, every one of these angles in standard position has what we are going to call a reference angle. The reference angle is the acute angle that's formed by the terminal side of the angle. So it always has a terminal side, remember. It's going to be the angle between the terminal side of the angle and the x-axis. We'll call that the reference angle. So I want to show you what this looks like in each of the quadrants. So I'm actually going to start in quadrant 2, this one right here, and then we'll look at each of the other quadrants as well. So if I have an angle that has its terminal side in quadrant 2, here's the terminal side, I'll make it nice and fat. The reference angle for the angle 120 degrees as an example, is the angle between the terminal side and the closest x-axis. So it would be this angle that is shown marked in green on the board with the star. That would be the reference angle. We often might want to know the measure of this reference angle, and the best way to find the measure of the reference angle is to actually just use a little bit of logic. So the angle that we're looking at the example of right now is 120 degrees. The reference angle is essentially the difference between that 120 degree angle and 180 degrees would get us all the way to here. So that means our reference angle is going to be 60 degrees, because 120 plus 60 will give me that full 180, that straight angle. Okay, let's look at an example in quadrant 3. In quadrant 3, I have the angle shown 220 degrees. So 220 degrees is there. Here's the terminal side. So the reference angle for 220 degrees is going to be the angle between that terminal side and the closest x-axis. So it's this reference angle, again shown in green. Well, if I wanted to know the measure of this reference angle, well, that entire angle shown in red is 220 degrees. Well, this portion of it is 180, so our reference angle is essentially the difference between those two. So you could think of it, oh, whoops, I wrote 200 instead of 220, sorry. You could think of it as the difference. Wow, I did it again. I give up. Here we go. 220 minus 180, which would tell us that that's a 40 degree reference angle. We'll label it inside there. So again, I figured out that it was 40 because this portion of it is 180 up here, so I knew it had to be 40 more to make the total 220. Let's look at one in quadrant 4. If my angle is it has its terminal side in quadrant 4, like this example is 315 degrees. We've rotated lots. So the reference angle is going to be the angle between the terminal side of my angle, 315 degrees, and the x-axis that is the closest. So the reference angle is this one shown in green. Well, a full rotation would be 360. So a way to find the measure of this reference angle would be to think about how much more you need to rotate to get to 360 degrees. So you could think of it as the difference between 360 degrees and our 315 degree angle. So our reference angle for this particular angle is 45 degrees. And then finally, if we look at quadrant 1, I have this example 65 degrees here shown. It has the terminal side in quadrant 1. The reference angle is between the terminal side and the x-axis. And you can see that the reference angle and the angle itself are actually the same. So the reference angle in this quadrant in quadrant 1 is always the angle itself. So for this particular example, it's a 65 degree reference angle. Sometimes people will remember the reference angles, the reference triangles, as being part of this bow tie shape to help you choose the right one. It's always, 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 the reference angle is always measured to the x-axis. So that's why it makes this bow tie shape. Never, ever, ever do you measure a reference angle to the y-axis. Always the x-axis. Okay, so now we're going to practice sketching some angles and finding the reference angle. So the first angle we're going to sketch is 230 degrees. So if I'm sketching 230 degrees, remember that we start on the positive x-axis, and for a positive angle we rotate sort of upward. So I'm rotating, this takes me to 90, keep rotating all the way to 180. We're trying to get to 230, so we need to go a little bit more. So this would be my angle, 230 degrees. If I had rotated all the way to here, that would have been 270 degrees. So now we've sketched the angle. I want to know how big is this reference angle between the terminal side and the x-axis. This is the reference angle. Well, this portion of that angle is 180, so the reference angle is just a little past that 180, and in particular, we would have to go an additional 50 degrees to get to that terminal side. So our reference angle is 50 degrees. So essentially, the way you might think about that is that it's the 230 degrees minus that 180. Okay, let's try a negative angle now. So we still start on our positive x-axis. We're going to rotate negative 330 degrees. So as we rotate, it's 90, negative 180, negative 270, and we would need to continue going another 60 degrees to get to negative 330 degrees. So our reference angle would be between the terminal side and the x-axis. So our reference angle is here. Put a star on it. Okay, so if we want to know how big this reference angle is, well, for this particular angle, it looks like it's how much more we would need to rotate to get to 360 degrees. This is a, whoops, I don't know what I'm writing. Sorry. This is a 30-degree angle, because I would need to go 30 more degrees to get to 360. Now, one thing about reference angles that I didn't mention yet, because I wanted to wait until we saw an example, is that reference angles are not ever negative angles. They're always positive angles. It's always just the size of that angle. A lot of times they're not in standard position. Like this reference angle over here is not in standard position. So we don't really talk about them as being negative or positive. They're just always positive. It's just the size of that angle. We're not thinking about which direction we're rotating with reference angles. Okay, let's try a couple more. 135 degrees, so if we're starting here, this would take us to 90. We need to go about 45 more to get to 135 degrees. So here's our terminal side. So the reference angle for this angle 135 degrees would be the angle between the terminal side and the x-axis. So it'll be here. In this quadrant, you almost have to think about how much farther do you need to go to get to 180. So you could think, how much farther do I need to go to get to 180? And you might decide that it would be 45 degrees. That's the reference angle. Okay, one last one of these. We want to sketch the angle negative 240. So starting on our positive x-axis, that's our initial side. We're going to rotate in this direction. That's negative 90, negative 180. I need to go 60 more to get to 240 degrees in the negative direction. So to find the reference angle, oops, I'm going to move that negative 240 because it's kind of in an awkward spot. The reference angle will be between the terminal side and the x-axis. So our reference angle will be this one shown in green. Well, this portion of it was 180 degree rotation. We're looking for the reference angle, so the reference angle is how much more did we go to get to 240? And that would be 60 degrees. You could think about taking away that 180 degrees to find that angle. And again, we don't really think about it as the directional one. We're not looking for if it's a negative 60 or positive 60. We're just saying that the size of the reference angle is 60 degrees. Okay. So now that we've defined an angle in standard position, we're going to look at this definition of trig function for a general angle. So if theta is an angle that is in standard position, no longer limited to angles and right triangles, if we look at that terminal side and we choose a point on it, so we have this point P that's on the terminal side. And the coordinates of P we're just going to say are x, y. You can find the sine, cosine, and tangent of theta by using this reference triangle using x and y. So we go back x and up y in this case, or you could go in another direction depending on your signs. So the terminal side and your x coordinate and your y coordinate build this little right triangle. The length of the third side of the triangle, the hypotenuse, you would find using the Pythagorean theorem. And so if we're using our reference triangle and the reference angle in that triangle, you can define the sine, cosine, and tangent for that reference triangle. So the sine would be the opposite side, so it's y over the hypotenuse, r. So that's our first trig function. The sine of theta is y over r. For cosine, from this reference angle, it would be the adjacent side over the hypotenuse, so x over r. And for the tangent, it would be the ratio y over x. That's the opposite side over the adjacent side. So y over x. Now we can't divide by 0, so x cannot be 0. So that's the way of defining the sine of this angle theta. So theta is not inside the triangle anymore. We have to use the reference angle in the triangle to define the sine, cosine, and tangent. So let's look at an example, because sometimes when you start doing with numbers, it makes more sense than when it's a definition with just x's and y's. So here's our instructions. The terminal side of theta in standard position contains the point -2, -6. We want to find the sine, cosine, and tangent of theta. Well, if we start at the origin and we want to get to that point -2, -6, we would go back 2 and we would go down 6. This is the point -2, -6. It tells me that that point is included on the terminal side of the angle. So here is the terminal side of the angle going through that point. So we're talking about this angle theta in standard position. So it starts here at the positive x-axis and rotates over to our terminal side. Well, again, theta is not in a right triangle, but we can use this reference triangle that we built. I like to build the triangle by following my pencil path, starting at the origin to point P. So back 2, down 6. It creates a little right triangle. So we're going to use this reference angle as we're thinking about our sine, cosine, and tangent. The sine of theta is going to be the opposite side, -6, over the hypotenuse. Oh, we need the hypotenuse. You might have noticed on the other slide that it labels the hypotenuse r. That's just common convention. It's just most often used as r, but you can think of it as c if you feel better about that. So we need to find the length of this hypotenuse in order to finish writing our sine. Well, if we use Pythagorean theorem, it would be -2 squared. And the negative is really just telling me the direction in this case, that we went back 2 instead of forward 2. So -2 squared, make sure that -2 is inside the parentheses, plus -6 squared is going to be equal to the hypotenuse squared, and we're going to call the hypotenuse r. Well, if I calculate -2 squared plus -6 squared, that's equal to 40. Well, if r squared is 40, I can take the square root of both sides of that equation to find out that r is equal to the square root of 40. Now that happens to be a radical that can be simplified. Root 40 is the same as the square root of 4 times the square root of 10. And we know the square root of 4, that's 2. So we would say that r is 2 root 10. Now I'm going to label that over here. 2 root 10. Okay, so now we can finish writing our sine. Sine was the opposite over the hypotenuse. The hypotenuse is 2 root 10. Now that is the sine, but we could simplify it a little bit. And it won't always need to be simplified, but it sometimes will be. So the first thing I might notice is that I have a -6 over a 2. So we could reduce a factor of 2, and that could be just a -3. So now we have -3 over the square root of 10. If we simplify that a little bit further, what we would want to do is rationalize it. So we now have that the sine of theta is equal to 3 root 10 over 10. And don't lose, like I almost did, don't lose your negative. So here's our sine. Now we can find the cosine. Cosine of theta, again, we're using our reference angle right here. Cosine would be the adjacent side over the hypotenuse. So it's -2 over, the hypotenuse was 2 root 10. And once again, we can reduce that a little bit. The factor of 2 can reduce. So it's like a -1 over the square root of 10. And we can rationalize that. So we have now that the cosine of theta is equal to negative root 10 over 10. And finally, we want to write down the tangent. The tangent is the opposite over the adjacent. So in this case, that is opposite is negative 6 over negative 2. And if we reduce that, we find that the tangent of theta is negative 6 divided by negative 2 is 3. So we have found our sine, cosine, and tangent. Let's try another one. It is a hard process, but don't worry, you will get the hang of it. So we have now a terminal side of theta that contains a point 1, negative 5. So if I think about drawing this angle, I like to follow my path from the origin to that point. To get to the point 1, negative 5, I go over 1, and I go down 5. I kind of like drawing on coordinate planes that don't have any numbers, and I can just go as far as I want. So that takes me to point P, which is the point 1, negative 5. So that point is contained on the terminal side of theta. So here is my terminal side. The angle theta is this really quite big angle. It's even larger than 270. So we've drawn, by following that point, the path to that point, we've drawn our little right triangle. Well, if we're going to write down the sine and the cosine, we are going to need the hypotenuse of that little triangle. So let's calculate our hypotenuse. It will be 1 squared plus negative 5 squared is equal to r squared. Well, 1 squared plus negative 5 squared is equal to 26. Make sure you have your negative 5 inside parentheses. And finally, to find our length r, we're going to take the square root of both sides. So we have r equals the square root of 26. And lucky enough for us, that one cannot be simplified. You could try a couple things. You could try maybe thinking about if 4 or 16 would go into 26, but 26 cannot be simplified, or the square root of 26 cannot be simplified. So we've got our hypotenuse. I'm going to add that to my drawing, square root of 26. Okay, now we're ready to write down our trig ratios. The sine is the opposite over the hypotenuse. So that's negative 5 over root 26. That one's not too hard to rationalize. We times by root 26 top and bottom to get that the sine of theta is negative 5 root 26 over 26. Now we can write the cosine. Cosine of theta would be the adjacent over the hypotenuse for this reference angle here. So the adjacent is 1 over root 26. We can rationalize that so that it is in simplest form. So we get that the cosine theta is root 26, because 1 times root 26 is root 26, divided by 26. And one last one to find the tangent. The tangent tends to be the easiest. So for the tangent, we want the opposite over the adjacent, negative 5 over 1, which is negative 5. And we have found all of our trig ratios for this, this angle theta. Now remember, we found these ratios are for this angle, this really large angle, so it's kind of cool. All right. Well, I want to look at a couple of special angles now. I don't want you to panic if you have a hard time with these next two. We're looking at some very theoretical math here, and so I wanted to look at these two special cases, but don't panic too much about this if this seems difficult, because it is a difficult concept. So the terminal side of theta this time is going to contain the point negative 6, 0. Here's the point negative 6, 0. So if that's the terminal side and this is the initial side, we're talking about this angle. So we're talking about the angle 180 degrees for a minute. Well, first of all, there's not a triangle. There's not even a reference triangle this time. Well, I think it can be at least a little bit interesting to think about a triangle like this, where the height, so my path to this imaginary point here would be that I went back 6 and I went up 0. So I'm exaggerating and making that 0 seem kind of big, but we're gonna still say that it's 0. So this is the triangle that we're kind of looking at or thinking about. It's certainly not a real triangle because a real triangle can't be 0 high, but that's the best way that we could maybe try to imagine this situation. So I could, for this sort of not real triangle, find the length of this hypotenuse, and I would find it the same way as I have always found the hypotenuse, which is using the Pythagorean theorem. So it would be 0 squared plus negative 6 squared is equal to r squared. Well, 0 squared plus negative 6 squared is 36. And so when I take the square root of both sides to find out what r is, I get that r is equal to 6. So I'm going to add that to my drawing. So I have two sides of my triangle. I have a side that is negative 6 and a side that is 0, and the hypotenuse now I find out is 6. So if I use this idea of this triangle with 0 height and this reference angle here, the sine would be the opposite side, which is 0 over the hypotenuse, which is 6. And that's actually our definition of sine. I have it really small up here. It's on your paper on the top. The definition is to take the y value and divide it by the r value. And that's exactly what we're doing with this sort of not real triangle because it has 0 height. We're taking this y value, how far we went up, and dividing it by this r value that we calculated. So the sine of theta is 0. And you could verify that in your calculator. We know what angle that we're looking at here. It's 180 degrees. So if you type in your calculator sine of 180 degrees, your calculator knows, for the reasons that we've shown here, that that's equal to 0. The cosine of theta for this triangle, I would think about the adjacent side over that hypotenuse. And again, the definition tells me that it's the x value over the r value. And that's exactly what we're doing when we're thinking about the adjacent and the hypotenuse, is we're taking that x value and putting it over our r value. And that would be -1. And again, your calculator totally knows that. We're talking about 180 degrees here. This, I wrote sine, sorry. The cosine of 180 degrees is -1, and you could put that in your calculator and it would tell you that. The last one is the tangent. So if we thought about the opposite side of that little triangle over the adjacent side, it would be 0 over -6, which is 0. And again, if you used your calculator to verify that, the tangent of 180 degrees is in fact 0. And that was our definition, to put the y value over the x value. So on this next one, I think it's very difficult to draw the little pretend triangle, because this time the pretend triangle is 0 wide. It's harder to draw. So I want to look at this one from the perspective of our definitions, which are here, and you have them on the top of your paper, hopefully. So this time we have the terminal side of theta in standard position containing the point 0, -4. So our x value is 0 and our y value is -4. So we're talking about this angle theta because here's our terminal side. So we're talking about the angle 270 degrees. Well, if we calculate our R value the same way we've been calculating it, it would be 0 squared plus -4 squared equals R squared. And that would be 16 is equal to R squared. And so when we take the square root, we find that R is 4. So we have an X value of 0, we have a Y value of -4, and we have an R value of +4. So if we use our definition for the sign, it's Y over R. That would be -4 over 4. Here's my Y value, here's my R value. And if we simplify that, it is -1. And again, your calculator totally knows this. The sine of 270 degrees is -1. For the cosine, we would put by the definition here, we would put the x value over the r value. That would be 0 over 4, which reduces to 0. And again, that's when you can verify in your calculator the cosine of 270 degrees is in fact 0. And finally, the tangent, our definition tells us that's going to be the y over the x. So if we put the y over the x, cannot divide by 0. So this one is undefined. And in fact, if you put that into your calculator, the tangent of 270 degrees, it is in fact an error because it is not defined. Okay, so I want to do one last type of problem with you. You know, our calculators, like we just verified on those problems, our calculators know these sine and cosine values, even for angles that are obtuse and not included in a right triangle. So we can actually use our calculators and this idea of reference angles to find out what theta is if we know something about it. And so we're going to use this idea of a point on the terminal side of the angle. So this says that we want to find the measure of the angle theta. It's in standard position, and the point -5, -7 is on the terminal side of theta. So if I was drawing my path to that point P, I would go back 5 and down 7. So this would be my point P right here. So if I drew the terminal side of the angle, we would be looking for this angle theta. I want to know how big it is. So I can see from my drawing that it's greater than 180 degrees and less than 270 degrees. It's in the third quadrant. So we're going to use this reference triangle and this little reference angle here to find the value of theta. I'm going to label the reference angle alpha. So if I'm finding this angle theta, I can use the tangent. Now I pick the tangent because from this little reference angle here, the -7 is the opposite side and the -5 is the adjacent side. So I could write that the tangent of theta is equal to -7, the opposite, over -5, the adjacent. Well, if you remember back to our last lesson, we talked about how to find the missing angle here, and the way that we talked about doing that was to take the inverse tangent in this case. So we're going to do the inverse tangent of -5 or -7 over -5. And we find, or our calculator tells us that theta is 54.6 degrees, or 54.5 degrees. Well, that's not theta. Theta is this red angle. Theta is bigger than 180 degrees. When you do this inverse tangent in your calculator, the calculator's not actually giving you theta. It's actually giving you the reference angle alpha. So we know that this angle is 54.5 degrees. So to figure out what theta is, we've got to think about how to get theta from that reference angle. Well, theta has 180 degrees of rotation here, and then it has 54 more. So we actually just need to add that 180 degrees to this reference angle to find out what theta really is. And when we add that 180 degrees, we find that theta is 234.5 degrees, which makes sense because I knew from the picture that it had to be between 180 and 270, and this angle fits the bill. So that's our angle theta. Let's try just one more of those. This time, our terminal side is going to include the point 4, -2. So if we think about our path from the origin to that point, we would go over 4 and down 2. Here's our point P. So that would make the terminal side of theta this line, or ray, I guess. So the angle we're talking about is this very large angle. Let's see, I'm going to draw it in red to make it bigger, more noticeable. This is theta. So we can use this reference triangle to figure out how big theta is. I'm going to write it as the tangent of alpha this time, since I know that it's not going to give me theta straight away. So the tangent of alpha, well, if I'm looking at this little reference triangle, this would be the opposite side, and this would be the adjacent side. That's why I picked tangent. So it would be the tangent of alpha is -2 over 4, the opposite over the adjacent. Well, to solve for that reference angle, I would take the inverse tangent. And if I allow my calculator to calculate that, I find that this reference angle is -26.6. So it's giving me a negative angle here. It's the size 26.6 and it's rotating this backwards direction. So if I want to figure out theta from that, well, a full rotation would be 360. We are this angle, this reference angle, less than 360. So to figure out theta, we would subtract that 26.6 from 360. So we find that our angle theta is 333.4 degrees, which makes sense. You can see from the picture that it's got to be more than 270, less than 360, and 333 is right there where it's at. So that is our angle theta. Okay, that's it. It's a little bit hard, I know. It's very theoretical. You're going to do great, though, and if you need some help, come in, and I would love to help you get it squared away in your brain. That is all.